last time we proved this theorem due to Shamir. We showed that IP equal to P space. So any problem that can be solved by interactive protocol can also be solved in P space, and any problem in P space has an interactive protocol. So the hard part here was to actually show that quantified Boolean formula, which is a complete problem for P space, that has an interactive protocol, right? So we showed that, and then using that theorem we will show that if exponential time has circuits, then exponential time solvable problems also have a one round Merlin-Arthur protocol, okay, which we don't believe any of these conditions, any of these statements, but this lemma will actually give a connection. So in other words, you can also say the contrapositive, which is that if exponential time problems don't have Merlin-Arthur protocol, then they also don't have circuits. So we assume that exponential time is in P/poly, and we will show that an immediate or a easy consequence of that would be that any exponential time solvable problem, say L, with this Turing machine N, it can be, the steps of Turing machine N can be encoded using quantifiers. They exist for all quantifiers. So let us see that encoding. So the jth bit in the ith configuration right, remember that when a Turing machine starts its steps, the computation, then in any moment of time it is in a configuration. So configuration means where is the head, what is the state, and what is there on the tape. So the jth bit in the ith configuration of N started with input X is computable in exp. This is the hypothesis, right? This just follows from the hypothesis that L is in exp. So this implies that there exists a poly-sized circuit C, which will take X, I and J in binary, that computes this bit, right? So this is because of the hypothesis that X is in P/poly. So hence, once you have assumed that jth bit can be computed in exp, then there is in fact a circuit that can also compute it, and the circuit is only poly-size in X. So which is the same as saying that if X is a yes string, then and only then there is a circuit such that for all I, J, Cxij to Cx I plus 1j is a valid step. So what are we saying here? So we are saying that X is a yes string if and only if there is this circuit C, which is small sized, such that for every I and j, so Cxij computes the jth bit, right, in the ith configuration. So going from ith configuration to I plus 1th configuration, this is one step of the Turing machine, and the jth bit respectively of these two configurations is being verified. And this verification, whether the jth bit of when you go from ith configuration to I plus 1th configuration, whether this is correct, this can be checked simply by using the control of n, right? So n is a Turing machine which has a finite control. So one step is very easy to check. So this thing in the square bracket, this can be checked easily. And there is in fact a circuit C which will be able to check. The claim is that it can check for every I and j. So it can actually check the whole computation. And the computation has exponentially many steps. Right, this is the property of the circuit C. That's how we write in there exist for all quantification. So this means that L is in sigma 2. And L was any language in exp. So you have actually shown that exp is in sigma 2. And sigma 2 itself is trivially in exp, right? So this means that exp is equal to sigma 2. Right? This is a very strong conclusion. It's a very strong statement that exp is equal to sigma 2. But the hypothesis was also very strong that exp is in P/poly. From that you are getting this. So let us continue the connections. We also know that sigma 2 is in P space, which has been shown to be IP, which is trivially in exp, because interactive protocol can be checked, simulated in exp. And exp we have shown to be equal to sigma 2. So this means that all these containments are equalities. So this means that P space is equal to IP is equal to exp. Exp was given to have circuits P/poly. So in particular you have deduced that P space, or more interestingly IP, what you have deduced from here, this is that IP, it has poly-size circuits. Okay, so now the way we will use this fact or this conclusion is that in any interactive protocol, Merlin now can be eliminated and replaced by a circuit. Okay, so Arthur can just talk to a circuit in the protocol instead of this advisor Merlin. So this is what we learned from here. So Merlin can be seen as a P-space machine. Hence, now it can be simulated. By a poly-size circuit family. Let's call it Cn. Okay, so this Cn is basically Merlin. You replace Merlin by this circuit Cn, which is basically n is the input size x. So for that particular input size, Merlin can be replaced or simulated by the circuit, and Arthur will now just invoke this as an oracle. So this suggests a one-round protocol to convince Arthur that X is in L. What is that protocol? Well, Merlin will just send the circuit Cn to Arthur, and Arthur can now play with the circuit. Arthur doesn't need Merlin. That's the one round. Okay, that is the simple trick. So Merlin sends circuit C claiming it to be Cn for n size of x, and Arthur can run the protocol. Using C. Instead of challenging Merlin. Right, so what has happened here is that Merlin, which in the definition of IP or MA or AM, Merlin is all powerful. Merlin just gives answers whenever challenged by Arthur, and then it is up to Arthur to verify. But here, because of the strong hypotheses, we have been able to show that actually Merlin is only as good as a polysize circuit. Okay, so now in the protocol, this circuit is presented to Arthur, and then Arthur can work on his own, which means that L is in MA. So this protocol implies that L is actually in MA, and L was any language in EXP. So actually EXP is in MA. MA is obviously in EXP, so this means that EXP is equal to MA. Okay, that finishes the lemma. That if you assume exponential time problems to have small circuits, then EXP has a single round protocol. Let us now move to the final lemma. So the final lemma that we'll present so we'll see the proof when we start or when we do pseudo-random generators. So this lemma says, well, it was shown by Impagliazzo, Kabanets and Vigderson. So here the hypothesis is even stronger than before, which is next is in P/poly. Assume that. Then what can you deduce? Nobody believes that next can be solved in or using poly-sized circuits. Because exponential time problems are already hard enough. Next could solve another level of exponential hardness, right? So we don't expect these doubly exponential time problems to have such small circuits. But if you assume this, then what you get is next equal to exp. Okay, so this non-determinism can be eliminated at the exponential level. Okay, next equal to exp. That's the conclusion. If you assume this absurd containment. So we'll prove this towards the end of the course. For now, you just remember this lemma, and let us now finish the proof of our PIT lower bound connection, which we stated long time back. So we stated it here. This Kabanets and Impagliazzo theorem, right? That if BPP is equal to P, then either NEXP doesn't have circuits or permanent doesn't have circuits. So former circuits are Boolean, latter circuits are arithmetic circuits, right? So let us finish this theorem. So let's finish. The proof of PIT lower bound theorem, which is that if PIT, so polynomial identity testing, if it is in P or if BPP is equal to P, then either NEXP is not in P/poly or permanent doesn't have arithmetic circuits polycized, this arithmetic P/poly. Okay, what is the proof? So now the things that we have developed till now, the tools and the lemmas, the complexity classes, using them the proof is actually very easy. So we'll just assume all these three things: PIT in P, NEXP in P/poly, permanent in arithmetic P/poly, and we will deduce a contradiction, simple contradiction. So suppose PIT is in P and at the same time NEXP is in P/poly. So then we have proved a lemma. I think our first lemma was, assuming these two things, you can deduce NEXP equal to exp. Okay, let us verify this. So this is just NEXP in P/poly. This is just this blue statement. So suppose NEXP is in P/poly, then you get from the previous lemma that NEXP, exp both are equal to MA. Okay, this is the lemma which we have not proved, we just stated. Also, there is a theorem called Todas Theorem, which, so remember that MA is in the polynomial hierarchy, and then there is a theorem called Todas Theorem which tells us that polynomial hierarchy is in permanent. So using permanent as an oracle, you can solve anything in polynomial hierarchy. Okay, this is called Todas Theorem. So this is a class between PH and P space. So this NP, NP to the NP, NP to the NP to the NP, all these classes, they actually can be computed by just permanent, using it as an oracle. So all this implies that NEXP is in P raised to permanent. Okay, let's remember this, that NEXP is in P raised to permanent. Now assume that permanent is in arithmetic P/poly and PIT is in P. If you assume these two things, then there was a lemma which I think we proved it first. The first lemma, which tells you that P raised to permanent has NP proofs, so permanent can be verified efficiently, right? The idea was just that permanent, you will guess the small arithmetic circuit and then use PIT after expanding permanent row by row recursively. So that told us that P raised to permanent is in NP, so which together with pH in or next in p raised to permanent implies that next is in NP as well, which contradicts. It contradicts the non-deterministic time hierarchy. So non-deterministic time hierarchy theorem says that if you have a complexity class where the non-determinism is function f, and then there is another non-deterministic time complexity class using time with function say f square, okay, then you get a strictly bigger class. So more time means you can solve more problems. That is contradicted by next equal to NP. So this contradiction means that one of the three assumptions is false. Thus, PIT in P will imply either next not in P slash poly or permanent not in arithmetic P slash poly. Okay, so this finishes our big theorem. It required defining all these new complexity classes by different means and proving connections between these impossible statements. So what we have learned in the end is that if you can de-randomize, so if you can de-randomize, which means that if BPP is equal to P, then there are lower bounds. So either next will not have circuits or permanent will not have circuits. Okay, so this is a very interesting connection. And remember that we had also shown earlier, we had shown using a simpler proof that if you assume black box PIT in P, then you actually get explicit polynomials which are exponentially hard for arithmetic circuits. Okay, so both these theorems are excellent examples of connection between existence of an algorithm versus non-existence of circuits, and hence non-existence of algorithms. So in the rest of the course we will discuss both these high level concepts. One is this de-randomization, which means that you design pseudo random generators so that randomization can be eliminated. So we will discuss that, what are the possibilities, constructions, objects related to this. On the other hand, we will also see what we can do or how can we prove lower bounds, circuit lower bounds, and mainly Boolean circuit lower bounds. Okay, so let us start with that. And proving lower bounds for in the circuit model is actually far stronger than proving it over Turing machines. Okay, because if there is a fast Turing machine, then there are also small circuits. So if you show that there are no small circuits, then you are also showing that there are no fast Turing machines. So obviously the prime motivation for this is it's believed that NP is not equal to P. right, which is saying that problems whose solution verification is easy, they may not be easy to solve. Okay, given a solution you can verify, but that doesn't mean that you can actually find the solution. So that is a philosophically it's a self-evident fact, but mathematically how do you show it, right? So that's an open question. So one way to show it is to show something stronger. To show a stronger result that SAT is not in P/poly. Okay, so first statement or first conjecture is SAT is not in P, but that is implied by SAT is not in P/poly, right? So SAT doesn't have poly-size circuits. And this seems to be a better formulation because it's a more algebraic question. So maybe we can study it by developing or using mathematical tools. Okay, it is still a statement about Boolean functions, but the circuit has AND or NOT gates, and maybe you can simulate it. You can simulate it algebraically, and then maybe you can use algebraic tools as well to prove this. So this approach was tried. In the 70s and 80s. And lower bounds for special circuit models. Were shown. Okay, but only for special. So till now, obviously no general circuit lower bound results, but for special interesting circuit models, this approach was implemented. And this is where the probabilistic method part in the course title will enter. So probabilistic methods were used to do this. So we will now start walking on this path and prove some very interesting lower bound results using very interesting algebraic and probabilistic tools. Okay, so to exhibit the implementation of these ideas, the complexity class that we will use is called AC0. What is AC0? So we want to look at restricted forms of Boolean circuits, and the first thing we restrict is depth. Okay, so let us restrict the depth to a constant. Let's say we are looking at Boolean circuits where the depth is 100, okay, or 200 or 1 million or 1 billion. So it can be any constant, which means that it is not allowed to grow with the input size n. Okay, with respect to the number of variables n, depth is constant. So AC0 is the set of those problems, Boolean problems, so which means language is L, such that there exists poly n size constant depth Boolean circuits for L. Solving L. So the key thing is poly in size, constant depth, and Boolean circuit. So what are the problems that have AC0 solutions? Boolean circuits have gates and or not. Our methods actually will require one more gate called the modular gate. So mod m, which is takes m bits, gives 1 bit. Right? Of course, it's a binary function, and what it does is it will just check whether the sum of the m input bits, whether it is divisible by m or not. Okay, it's just kind of checking the sum mod m. So x1 to xm are the bits, and the answer will be 1 if the sum of xi's is not 0 mod m, 0 otherwise. So that's the modular gate. Okay, and so in AC0 you can also introduce these mod m gates. M is a constant, okay, so m will not depend on the input size, it's a constant. You can think of mod 2, mod 3, mod 5 and so on. You can also think of mod 4, mod 6. So when you introduce these gates, then the circuit is called ACC0. So AC0 with counters. So this is now the collection of those problems, Boolean languages L, such that there exist poly in size, constant depth, Boolean circuits using mod m gate. And solving L. So ACC0 is AC0 with the counters, but in particular it counts the values mod m. Size should be polynomial, depth should be constant, and circuit is Boolean. So everywhere only 0, 1 is used. So the question you should ask at this point is what about AC0 and ACC0 mod 2, okay, which is equivalent to asking where is mod 2? Is mod 2 in AC0? So in constant depth, can you compute parity? Right, mod 2 is parity. Meaning, given m bits, whether the number of ones is odd or even. When it is odd, answer is 1. When it's even, the answer is 0. So could that value be computed? Could that bit be computed, parity bit, in constant depth? It's not immediately clear, but if you think about it, then it seems that you have to computing the sum and also division mod 2, right? And you have to do it kind of n times, or you have to do it in a way which is dependent on n, right? Because it's a very sensitive, the function of parity is very sensitive on, it's sensitive on each and every bit. So it changes by flipping even a single bit. So it is sensitive to each of the n bits or m bits, n bits. In this case, we'll think of inputs as x1 to xn. So you have to look at each and every bit. That may be hard to do in just constant depth and polysize. Okay, so we actually believe it to be not there, and hence we believe AC0 to be different from ACC02. So this is what we will prove next. Okay, this is an amazing statement with an amazing proof technique. So in general, we suspect that mod m should not be in ACC0 m prime for co-prime m and m prime. So in particular, we suspect that mod 2 should not be in AC0, ACC01. Okay, so the question is whether ACC01 and ACC02 are different, and we would assume we would suspect it to be different whenever the two mod are different, and to be precise, co-prime. So that was shown by Razborov and Smolinsky. So for primes P and Q different, mod P is not in ACC0 mod Q. Okay, this is what we will prove, and the proof technique will be very interesting. So let us first mention the idea. So approximate an ACC0Q circuit by a polynomial over FQ. Okay, so we will so following the hunch that circuits are more algebraic, we will follow that and formalize it by replacing this circuit ACC0Q circuit by a multivariate polynomial mod Q. Q is a prime, so we are actually then working over this field, finite field FQ, and this polynomial will be approximating. Okay, it will not exactly compute the circuit, but it will approximate it well. So you can read it as ACC0Q circuits are easy to approximate by a polynomial. On the other hand, we will show that mod p does not have that property. So mod p function cannot be approximated easily over fq, okay, which will show that these two are different. Okay, so instead of doing this in the most general form, we will just fix p to be 2. So we will exhibit the proof for p equal to 2 and q equal to 3, and I leave the general proof for the assignment. Okay. So this will be a long proof, so let us break it into lemmas. So the first is the approximation part. Let C be our depth D, ACC 03, circuit on n inputs and size S. Then there is a polynomial in F3. Okay, so polynomial mod 3 multivariate. So which means it's so in the polynomial ring F3 x bar. F3 is the finite field with 3 elements. So there is a polynomial whose degree is not too high. To L to the D, L is some parameter. We'll fix it afterwards. So think of this as a low degree. Okay, so we are saying that there is a polynomial in F3 x bar which is low degree, which agrees with the circuit. So the circuit has variables x bar, x1 to xn. The same variables there are in the polynomial also. And this polynomial has low degree and it will agree with Cx, with the C very well. So it will agree on 1 minus S by 2 raised to L many inputs. Okay, so the input space is 0, 1 to the n, and out of this a good fraction. So 1 minus this S by 2 raised to L, which we can make small. So this is a big fraction. So for example, the polynomial may agree with this low degree, the low degree polynomial may agree with C on 99% of input space. Okay, it's not 100%. But it can be made pretty large, almost 100%. So that is a surprising fact, right? Why is this happening? How can you convert a circuit, Boolean circuit, into a polynomial which approximates this well and is low degree? So that is one lemma that we will show. The other lemma that we will show is the opposite for mod 2. So no polynomial in the same polynomial ring of degree smaller than square root n can agree with mod 2 on 99% of the input. Okay, so these two lemmas will together imply that mod 2 cannot be computed by in ACC 0, ACC 03. Why is that? So now if mod 2 has size S ACC 03 circuit, then by lemma 1 for a certain L we will get a polynomial, and that polynomial will have low degree lemma 2. Okay, so we will implement this. So suppose mod 2 has size S ACC 03 circuit, then by lemma 1 so in lemma 1 you will, the degree is L to the D, right, so roughly L to the D, and in lemma 2 the degree is square root n. So you basically want to match these two, which means L should be around n to the 1 over 2D. So that is what we do. So by lemma 1 for L n to the 1 over 2D and slightly smaller than that, 1 by 2, half of this, there exists a polynomial of degree less than equal to 2L to the D, which is at most, which is square root n. And whenever we use these expressions, we actually mean the closest integer, right? So something like this, the floor of this. So 2L raised to D will be at most square root n, and this polynomial agrees with mod 2. On 1 minus S 2 raised to L fraction of the inputs. Now lemma 2 says that whenever this happens, the fraction has to be small, right? So 1 minus S over 2 raised to L, this should be smaller than 0.99, which means that S has to be large. Larger than this, correct? So how big is L? L is around n raised to 1 over 2D, right? So this is actually bigger than 2 raised to, let us say, n raised to 1 by 2D by 3. Right? So you can pick n to be sufficiently large, and then the lower bound you are getting because of lemma 1 and lemma 2 together is S is actually more than 2 raised to n raised to epsilon, where epsilon is this constant, absolute constant 1 over 2D. Right? This is not polynomial size, this is exponential size. So you deduce that mod 2 cannot be in ACC 0, 3. Right, which also means that parity cannot be in AC 0, because AC 0 is even weaker than ACC 0, 3. So mod 2 or parity, it cannot be in AC 0. Okay, so this will finish our claimed theorem by Razborov and Smolinsky. And you can see that in this proof, you can take D to be non-constant as well. So it's slightly more than AC 0. So any depth D smaller than log n divided by this thing will work, where epsilon is a constant close to 0. This is because this n raised to 1 by d, you want this to be more than sufficiently bigger than log n, right? In that case, your S will become super polynomial. So n raised to 1 by d, we want this to be more than log n. Little omega log n, right? Should be asymptotically larger than log n. So 1 by d log n should be equal to omega log n, which is that d has to be smaller than log n by log n. Okay, that's the correct thing to say. So let me just correct this. So smaller than log n by log n. So if you take depth of your Boolean circuit to be just smaller than log n by log n, then the previous lower bound that you have gotten is super polynomial. Okay, so even circuits of that depth will not be able to compute parity. So now all that remains is to prove lemma 1 and lemma 2, right? So how do we show lemma 1? So lemma 1 is the approximator lemma and lemma 2 is the parity hardness or inapproximability lemma. So let us prove the approximator one first. So we construct an approximator in the polynomial ring F3 x bar for the circuit C inductively. Because the proof will be by induction on size. So which means that we will first convert AND gate approximator for AND gate, approximator for NOT gate, approximator for OR gate, and then build this one by one, gate by gate. Let's do that. So let G be a gate in C, in the circuit C at height h. And let us look at an approximator for G. So define of degree 2l raised to h such that G tilde at x bar equals G at x bar for most inputs. Okay, so we have to find this approximator G tilde. Or we have to design it. Looking at the gate G at height h, we will design it. So we will assume that we have an approximator for the inputs of G, and using that we will design for G tilde.